Hello, good morning and welcome dear students to Vista's e-learning and online educational platform. My name is Denzil, your physics tutor for class 11. So let's get started with today's session. Today's session is based on a concept which is called significant figures. This is a session 5 of the chapter measurement. Now, especially when it comes to dealing with error analysis, you determine the precision of a given instrument, and that precision of a given instrument has a certain least count. So depending on the precision, there might be a couple of errors plus or minus due to the various errors that we discussed in the previous session, which could be a random error or a systematic error. Now, if such errors can occur, is there any possibility that we can eliminate those errors? Certainly there are ways. Now, especially when it comes to dealing with number with certain precision, we need to stick to that precision of a given instrument. An example being, a ruler has a precision which is of 0.1 centimeter. I have to pick an ink. All right. 0.1 centimeter is a precision of your ruler, the scale that you use. This precision cannot be varied by writing 0.001 centimeter for a given instrument that is a scale. It would be false or wrong to write it this way because the right precision of the instrument is just 0.1 centimeter. So what if the number that you get is something like 0.124? Since you have to round it into a digit which is of 0.1, but since you have this number 0.14, so you have to use the rule where a precision is involved. And that rule is provided by significant figures. So measurement of a significant figure, let's say for a given measurement which is 123.3 millimeter, for an instrument that is ruler, you observe which is a 0.1 millimeter of a precision. So the first three digits what you observe are what are called as reliable digits. These digits tell you that you can be sure of this measured quantity being 123. On the other hand, the last digit is what is called the first uncertain digit. Uncertain because there might be an error due to its lower precision, which is of 0.1 millimeter. So together with the reliable digits as well as uncertain digits are what are known as significant digits or significant figures. In the following, which is 2.308 centimeter, has dash number of significant figure. So how do we identify for a given number how many significant figure exist? Now for this, we use couple of rules. We will answer this, but first let us understand what the rules are. Here are the rules. Rule number 1. All the non-zero digits are significant. Example, 1, 2, 3, which is a non-zero number, or it could also be 4. 1, 2, 3.4, non-zero numbers, so all of them are significant. Since all of them are significant, how many significant figures? Total of 4. A number which shows you the reliable digits as well as one uncertain digits. The next rule is all the zeros between the non-zero digits are also significant, no matter where the decimal point is, if at all. Example, 12.01. 12.01. there's a 0 in between two non-zero numbers. No matter wherever the decimal is placed, it could be placed here, first, second, no matter wherever it is placed. But if there's a 0 between two non-zero numbers, then the given number is significant. So how many significant digits? 1, 2, 3, 4. And why did I count 0? Because 0 between two non-zero numbers are also significant. So that's rule number 2. Moving on, rule number 3. If the number is less than 1, the 0 on the right of the decimal point but to the left of the first non-zero digits are not significant. So don't worry about this. I'll show you how exactly it works. 0 point, taking the same example, 0, 0, 2, 3, 0, 8. Now this 0 is obviously significant because there are two non-zero numbers beside it. But the zeros before the non-zero numbers, such as these zeros, and also the first place, which is 0 point, this makes an entire difference. If this is less than 1, if the first digit is less than 1, that is 0 in this case, then all the remaining zeros followed by it by a decimal are also non-significant. So if there are non-significant, how many significant figures exist here? Just 2, 3, 0, 8. So that the total of 4 significant digits. And the next point is the terminal or trailing 0 in a number without a decimal point are not significant. Example, 1700. These zeros which are followed by 7 are called trailing zeros. Okay, these are called trailing zeros. You can add more zeros. These are trailing zeros. These trailing zeros without a decimal point are non-significant. So you should not count them. Okay, trailing zeros. Then the trailing 0 in a number with the decimal point are significant. Example, 1.700. These are still trailing zeros, but the difference here is they are only followed by a decimal 7 and then trailing zeros. If so is the case, then these trailing zeros are significant. A big difference. Here, trailing zeros without a decimal. I have not introduced a decimal. But even if you put a decimal, there is no number. I'm not going to introduce any number. So which means these trailing zeros are not significant. But these trailing zeros are significant because they're followed by a decimal. All right. Now, one quick rule about rounding off uncertain digits. Now, we learned there are 3 reliable digits, an example which was 123 point. Let's go back and see what that is once again. Back. Oh yeah, 123.3. And also answer to this question, 2.308 centimeter has how many significant figures? By applying the rule, you see 0 is between two non-zero numbers. So you have 1, 2, 3, 4. So it has 4 significant figures. So now, rounding off the digits by taking this particular example, which is 123.3. Now, if I have to arrange this now currently has 4 significant digits. Okay, it has 4 significant digits, out of which 3 are reliable, 1 is uncertain. Now if I have to round this off to 2 significant digits, what am I going to do? is change this to two significant digits. How do I change it to two significant digits? If it is two significant digits, it should be only the number 1, 2. But then the number itself is 123. So how do I change it to 1, 2? Now the rule that we're going to apply is what we call as rounding off the digits. Rounding off the digits imply you look at how many significant digits you need. Here I need two significant digits. Choose the two significant digits, which is 1 and 2. Then I don't want the number 3 because if I have the number 3, what happens? It becomes 3 significant digits. So rather I will put a number 0. This 0 is called a trailing number or trailing zeros. Trailing zeros are not significant. So the given solution will just be two significant digits. Let's look into another example. 3.426. Total of 4 significant digits. Change this to three significant digits. To change it to 3 significant digits, now the rule is a little different. Have a look at it. 3.43. How did the number 2 change to 3? Now here's the rule. If the last number, if you're changing it to 3 significant digit, if the last number, okay, beside it, if the number is greater or equals to 5, beside the last number, then what you choose is the beside the last number. If the number is greater than or equals to 5, then the rule is you add +1. Okay, so here we have 6, which is greater than 5. Therefore, you add +1, which changes into 3. Similarly, if the number is 3.423, change this 4 significant figure to 3 significant figure, then you get the solution, which is 3.42. So what just happened here? The rule here is if the number is less than 4, if the number is less than 4, which is 3 in this case, which is less than 4, then it will be the number itself. Okay, you do not change. So you change, you add +1 when the number is greater than or equals to 5. Okay, so this rounding off, we will have a look at it later. But first, let us try to identify the significant figures in the following example. First one, how many significant figure in this particular example, which is 2100? You have one non-zero number, two non-zero number, and then trailing zeros. We don't care about the trailing zeros. So in this case, you have only 2 significant figure. How about this one here? This 0 is in between 2 and 8, which are non-zero. So you have 3 significant figure and 1 trailing zero, which we ignore. So total of 3. How about this one? 1 trailing zero, eliminate that one, and remaining is just 4. How about this? 40.2. There are 3 significant figures in this particular example. 0 is in between 2 non-zero numbers. How about this one? You may think that it should be only 1 because you have trailing zeros. You're wrong. These trailing zeros are after a decimal. After a decimal, trailing zeros are significant. Therefore, this is 3. How about this? 1, 2, 3, 4, 5. So total of 5 significant. This one. Now you would say that So there are trailing zeros. So 1, 2, 3, 4, 5, 6, total of 6. No. Why? Is the first number is less than 1. If the first number is less than 1, then followed by the other zeros, they are not significant. So remember that rule is first zero is less than 1 and the remaining zeros are not significant. Therefore, you get 201, which is 3. What if this number was actually 1.000201? What about this case? Now, that number is less than 1. What about this one? It is equals to 1.000201. What will be the significant figure? Well, now you have to include the zeros because the number is equals to or greater than 1, but here it is equals to 1. So it is 1, 2, 3, 4, 5, 6, 7. So total of 7 significant figures. If it is equals to 0, then this entire trailing zeros are ignored. How about this? Well, just like this, now you count the number of zeros. 1, 2, 3, 4, 5, 6, 7. 7. So this is how you identify the significant figures for a given example, which is this. Again, why are we doing this? Is to find the numbers that have the right precision of a given instrument. Now, when you make a certain measurement, it has to be precision of an instrument. It cannot be greater precision than whatever instrument that you're using. Imagine that the ruler that you're using has a precision which is 0.1. You cannot use the number as 0.125698. That shows you the precision of an instrument, and ruler is not that the case. It is just 0.1 or 0.2, 0.3, whichever number that you can follow by, but it has to be of a 10th place. All right. Now this question, which is 4.700 meter has dash significant figures. How many significant figures? Count 1, 2, 3, 4. 4. Now here's a quick question for you, a mind-boggling question. So here you have 4.700, which has 3 significant figures. Well understood. Now that meters is now converted into centimeters, so you get 470.0. Now even in this case, it is still, oh sorry, this is 4 significant figure. Why did I write 3? I have no idea why I wrote that 3. Okay, this is 4 significant figure. This is also 4 significant figure. Have a look at this. When a centimeter is converted to millimeter, you have only 2 significant figure. And this one into kilometer again has a 4 significant figure. So why is that changing from one unit to another? Significant figure changes. That should not happen. It should not happen where a significant figure changes as you convert from one unit to another. So what would be a better way to represent this so that the significant figure remains the same? The better way of writing is by a scientific notation. And the scientific notation is by the powers of 10. Now for a meter, we just write it as 4.700 meter. But if you have to convert the meter into centimeter, then you have to express in a form of an exponent, which is 10 square centimeter. Similarly, notice in all the following cases, when you convert them into exponents, the significant figure of a given instrument of this value remains the same, which is 4.700, 4.700, 4.700, 4.700. What has varied here are the exponents from 10 square, 10 cube, 10 to the power of minus 3, depending the conversion from one unit to another. This is how you can eliminate that confusion where converting one to another, the significant figure does not change in the following case for a scientific notation. So let's have a quick look at some of the operation that we use on a significant figure. Multiplication. Here you have an example where you have three significant figures. Here you have an example where there is 1, 2, 3, 4, 5 significant figures. And when you multiply the two numbers, this is the result you get. And the result what you have is 1, 2, 3, 4, 5, 6, 7, 8. 8 significant figure. I cannot have 8 significant figures when the initial product itself is 3 significant and 5 significant. It makes no sense. It's like the precision has automatically increased by itself. So I have to bring down the precision to a practical limit. So what we do is choose the lowest significant figure for a multiplication. The lowest significant figure is 3. So we have to put 3 significant figure to this. And how do you change this to 3 significant figures? That is where we use the rule called rounding off the uncertain digits. So 3 significant will be 1, 2, 3, and you see the number beside it. Is it greater than 5? Is it equals to 5? No, it is less than 4. And if it is less than 4, it is the number itself, which is 14.7. See, now you have 3 significant figures. Similarly, division also has the same operation. Initially here you have 4 significant figures. Here you have 3 significant figures. And here you have, oh God, I'm not going to mess with it. So let it be. I'm not going to count that kind of a situation. But what you need to understand here is that precision does not automatically improve by itself. So which means you have to lower it down to a precision that we are dealing with for a given instrument. So here also we choose for a lowest significant figure, which is of 3. So here choose 3 significant figures. That's 1, 2, 3. Check the number beside it is 8. 8 is greater than 5. So which means you can write this as 1.6 and then you add plus 1 to the adjacent. Hey, where did the point go? Okay, if you ever find the missing decimal point, you can return it back. So I'm going to write another decimal point here. Okay. So we have a vanishing decimal points. Put it back, whoever's stealing that. Okay. Don't steal the decimal points. All right. So you get 1.6 and then the adjacent will be 8 plus 1, 9. So now you have 3 significant figures of 1.69 where you have changed that adjacent 8 to plus 1 because of the number 8 which is greater than 5. Rounding off it's called. Okay. Quick rule in multiplication or division, the final result should retain as many significant figures as there are in original number with the least significant figure, and that is exactly what we did. The final result significant figure was matching with the least significant figure of the product or the division of the two numbers. All right. This is another example of a multiplication and division. So there's basically more of multiplication. So let's do it quick. It should be easy. 1, 2, 3, 4. There are 4 significant figures. 1, 2, 3, 4. There are 4 significant figures, but the product has more than 4. So we have to set it to 4 significant figures. 1, 2, 3, 4. But beside it is 9, which is greater than 5. So 8 plus 1. So you get 56.39, which is a 4 significant figure. Next question here. Here you have 4 significant figure and here you have 2 significant figure because there's point and a 0, so 2 significant figure. Since there's 2 significant figure, final product should also be of a 2 significant figure. So there's 139.5. 1 and 3 acceptable. I don't want the 9. What do I do? Now first, beside it, which is 9, you add plus 1 to the following, which becomes 1, 4. 1, 4, and then you add a 0. This 0 is a trailing 0. It does not count as a significant figure. This 0 does not count as a significant 0, which means the number of significant 0 is still 2, but this one is added to make sure it is in the same place as units, tenths, hundred. Unit place, tenths place, hundred place, units, tenths and hundreds. The 0 has no significant value. Okay. Now moving on to the next operation, which is addition or subtraction. So quick look at addition or quick look at this addition or subtraction. First addition, 12.012 plus 3.3. So you can write that here, 012 plus 3.3. Add the 2. Since there are no numbers after this, we still write it down, which is 1, 2, but the significant figure is restricted to only 2. Okay, and then you get 3.15. 15.3. How many significant figure? 2. Since there are only 2 significant figures, which is the least one, so I take 1, 5, and this I'm not going to bother because 1, 5 itself makes the least significant figure of 2. The same rule that we use for multiplication is rather. Okay. Now let's have a look at some of the arithmetic calculation. These are calculation where we find the area of a given rectangle. So you have length that is given, you have breadth that is given. For a length, there's a certain error. This is the error, 0.1 centimeter. Breadth, this is the error, which is of 0.1 centimeter. The error is rounded off to 0.6 centimeter. What is the calculation used here? How did 0.1 centimeter turn into a percentage? What is the calculation used? I'll show you the calculation. So the calculation that we use here is what we write, 0.1 divided by the total number, which is 16.2 times 100. Okay. By doing this, you will end with 0.6%. Now, it may not be exactly 0.6. I might want to show it to you by calculator. You will have 0.59 something or probably 0.7, which is rounded off to 0.6. Why is it rounded off to 0.6? Is because here you see the significant figure is 2. So here also you have 2. Similarly, you have the other case, which is of same case of 1.1, 0.1. All right, 0.1 divided by 10.1 times 100. Okay, and then you'd pick approximately, which is of 1%. 0.999. So 0.99990, which is rounded off to 1%. Okay. Now that we have the percentage of error, we calculate what will be the total error. How do we find the total error? Add the errors. 1 plus 0.6, which is 1.6% of error when it comes to product of 2, length and breadth. See, length times breadth, and you get this error, total error of 1.6%. And that 1.6% is then found what to be in terms of its actual value. The calculation again used here, I can show you the calculation, which is 1.6 divided by 100 times 163.62. Do this calculation and you get 2.6. Well, not exactly 2.6. You will have the followed decimals. Yes, you will have the following decimals, but you round it off to 2.6. Again, we use the rule which is rounding off. All right. So round it off to 2.6, which can then be rounded off to 3 centimeters square. So this is how you actually calculate for a given measurement what would be the area of a given plane figure when length and breadth is given, and how to calculate the error in total. Well, that is all for half for today. Do visit us at www.we-learning to get more details about the classes and also follow the previous classes. I will see you on the next session. In the next session, we shall discuss more about rounding off the digits and also significant figures. Take care, everyone, and have a nice day. Bye-bye.